All right, so today's extreme value theorem. This theorem is one we've already talked about, you've already used. It's kind of like intermediate value theorem, where it's like, in a continuous function, the function takes on all values between, a and b on that interval. Like it's continuous. It's like the definition of what continuous is. For every point, there's another one. There's always a value in between 2 points on a continuous function. So it's kind of like, do we really need to make that a whole theorem? But in math, that's what we do. We take things that are like laws or rules or theorems, and we articulate them so that brings clarity to kind of other things. So the extreme value theorem says this. As with all the other theorems, there are hypotheses that need to be met. So this one is, there's two things. So for any continuous function, frozen still, sorry. There we go. For any continuous function f of x, so it has to be continuous, and on a closed interval. So on a closed interval. So the function itself has to be continuous, and we have to be considering a closed interval, which means that the endpoints like this have to be, like they have to be valid. They have to be, they have to exist. You can't have like an open circle. If you have an open circle where the function sort of like comes up to this point, but you don't know how infinitely close it gets, it's not evaluated at that point, then this doesn't work. All right, so what this is saying is that if these two things are true, then there must exist, and again, this is going to sound very familiar because we've really used this theorem before, but we haven't named it. There must exist a value, so a y value, f of c, that is greater than or equal to all of the other values on f of x. So that means the function, even like you see here on the right here, so there must be a value, f of c, that's greater than the function or equal to the rest of the function. So really, that's saying there has to exist at least one absolute maximum. So there has to be an absolute max on this interval, and also there has to be a value f of d that is less than or equal to all of the other f of x. So there has to be an absolute min. There has to be an absolute min. So there has to be both. Now they can be the endpoints, or they can be any local max or min in the interval. Now, again, we've done this before because we've found the absolute max and min for a function with given endpoints. And we've actually done this all before, but there's actually a theorem that states it. Now, I'm going to give you a couple examples here where we'll be able to identify or not be able to identify max and min values given the extreme value theorem. So, for example, this first one, okay, so we have a closed interval. So these endpoints are closed, right? And it's continuous. There's no gaps or discontinuities at all. So this is continuous on a closed interval. So there exists a maximum. Here it happens to be this endpoint, and there exists a minimum. That's this endpoint. Okay? So that's like your typical function. This one here, okay, notice that it's continuous, but it's not a closed interval. So this is an open interval because of these open circles here. So we could have a absolute max, and we could have an absolute minimum, but it's not guaranteed by the theorem. So here's why. This appears to be the local max right here. Okay, so that's the max value. And this appears to be, so there appears to be a minimum value down here somewhere, but we can't identify it because it's an open interval. All right? So again, if you zoom in on this, like if you zoom, what happens is the function gets closer and closer and closer to this value, but you don't know where it ends. Here's the value right here. So you don't know how close it gets. It gets infinitely close to that value, and you can't identify that minimum point. Right? So it has to be a closed interval. There has to be an end point that's defined. So there could be a local max, but there isn't a local max and min guaranteed if the endpoints are open. Make sense on an open interval? Here's another example, the third one. So we do have a sort of a defined beginning point here, But this one, this is a crazy function, I just made it up, but this one has an open-ended point right here, an open-ended, kind of end to this part of the function, and this is open over here. And we have vertical asymptote, so it's discontinuous. So there is no absolute max or min guaranteed by the extreme value theorem. Again, it could be true that we can identify a maximum. This appears to be the max, right? It's defined, and that appears to be the highest point in the graph, but we don't know that for sure. We could guess. This appears to be, the lowest point appears to be somewhere over here, but because it's open-ended, we can't identify it. And plus, if this were a function where this was an arrow here, then we certainly wouldn't have either a max or a min anywhere. Okay? So it has to be continuous on a closed interval, then there has to be a max or min. Okay, so let's do this one question here together. And yes, this should look familiar. We've done this before, we just haven't named the theorem. So what is the absolute max and min for this particular function on the interval -1, 2? So you can jot this down as an example. I do have the steps on the side there. If you want to write those steps down, they'll be on the notes and on the video here for you. But these are the steps that you should follow. Just adjust this a little bit. Okay. All right. So first thing we want to do is confirm and state that the function is continuous on the interval, okay, and that it's a closed interval. So I should probably put that too. And a closed interval. Okay, let me put that in brackets. So if it's open interval, that doesn't work. So confirm and state that the function is continuous on the interval and it's a closed interval. So it's a closed interval, okay? And this is a polynomial function. So polynomial functions are always continuous. And that's going to be enough reason to say that it's continuous. Polynomial functions are continuous. And interval is closed. So just be sure that those are true, and you might be required to state that the hypotheses are true. All right, so the second one is find critical numbers, because again, if there is a local max and a local min, they may be the absolute max or mins. So we have to find the critical numbers and check the endpoints. So let's find our derivative. And I'm going to go through this a little bit quicker because this is something that we have done before. So find the derivative of that term and the derivative of this term, 12x squared. And good idea to factor so we can find critical numbers if we can. So we'll take out a 12x squared, x minus, x, yeah, that's x minus 1. Okay, so we have critical numbers, okay? X equals 0 and positive 1 are critical numbers. So if we did first derivative test, we could actually find out if those represent local max or mins. Okay, now we don't have to here. The question isn't asking about local max or mins. We've done that kind of question before. All this is find the values guaranteed by the extreme value theorem, so find the absolute max and mins. So we have those x values, that's great. We also want to consider the endpoints. So find critical numbers, we did that. Evaluate the function at the critical numbers. So f of 0 is going to be 3 times 0 to the 4 minus 4 times 0 cubed. So that's going to be just 0. And f of positive 1, that's going to be 3 times 1 to the 4 minus 4 times 1 to the 3, which is going to be 3 minus 4 is negative 1. All right, so these are two values that we need to consider. We also need to now evaluate the function at the endpoints. So the endpoints are negative 1 and 2. So f of negative 1 and f of 2. We'll evaluate those. So we have two more y values of 7 and 16. So we consider the possible local max and min values. Again, we don't know if they are, but the critical numbers here. We consider these values and the endpoints. And so the absolute max is the point going to be this value is the maximum. So f of 2 equals 16. That's the best way to write that, or you can put the 0.2 comma 16. And absolute min is, what's the smallest value here? Oh, looks like this -1. And so f of 1 being -1. So we compare all the values of the f of x's from the local max and mins and the endpoints, and the largest is the max and the smallest is the min. Express the max and min as points or in function notation. So this would be function notation, or here's the points, 2, 16, and this one, 1, -1. Okay, so let me just double check my work on that. You guys seeing anything that's a bit off, or is that looking okay to you guys? Okay, so those answers are confirmed. So that's extreme value theorem. Again, we've kind of been using this already. We just haven't named it. So you might get a question like this. Find the values guaranteed by EVT. That may be the exact question that you get on the AP exam. So then you have to know what the extreme value theorem is. You have to know what the hypotheses are. You have to be able to analyze the critical points, endpoints, find the local max and min, or the absolute max and min there. Okay, any questions? All right. All right, so I have an activity for you to do to summarize all of the theorems that we've been taking the last little bit, the intermediate value, Rolle's theorem, mean value theorem, and extreme value theorem, so we'll move to that. Phone is ringing.